All right, let's give it to him. All right, we're doing 4.4. This is on the mean value theorem. Mean value theorem is usually abbreviated as MVT. I know we've got a lot. We've got extreme value theorem. That's EVT. We have intermediate value theorem. That was IVT. And now we have MVT. I'm sure we have another VT somewhere in here. So part A is going to be on, it's called Rolle's theorem. So we're going to say f of x is continuous and it's differentiable on some closed interval a to b, and f of a equals f of b. Like we have here and here. We have here and here, if that's a and that's b. And we have here and here, if that's a and that's b. So it's continuous, it's differentiable on a closed interval, f of a equals f of b. Then there is somewhere where x equals c and c is inside AB, such that f prime of c equals 0. We've got three cases. We've got the flat line, we've got where there's an absolute max, and we've got the case where there's an absolute min. And we'll look at the three scenarios. We'll do a proof. Let's say k equals that value where f of a equals f of b. The first case is pretty straightforward. F of x equals k, so the derivative equals 0 for all x. Case 2, there exists an x naught in AB such that f of x naught is greater than k. And this notation over here, there exists. We often use this capital E backwards. I try to start slipping it in later on, get you used to seeing it. So we're going to assume there's some point in here that x naught where x naught is like greater than k. Like on this picture up here, x naught might be right here. So f of x naught is right there and is clearly greater than k. Since f of x, and we're going to do it on the open interval AB. We're not going to include the endpoints. Since f of x is continuous on that closed bounded interval, then there's an absolute max by the extreme value theorem, and it's got to be greater than k. So since x naught doesn't equal a and x naught doesn't equal b, we excluded them because we said open. Then the absolute max is not at a or b, and it means it's at some point c, somewhere in the middle. And that's where x of z yields the absolute max. So f of c equals absolute max. And Fermat's theorem said the derivative at the absolute max and absolute min was 0. So by Fermat's theorem, f prime of c equals 0, and we've showed it. Case 3, where there's an absolute min, it has the exact same proof. You're going to go up here. If you want to see the proof, you change everywhere it says max to min. You change this symbol to less than, and you're pretty much good to go. It's the same statement. It is important that it has to be differentiable on AB. The differentiable part implies that it's continuous, so that means both of those. If it's not differentiable, it may not work. Like, for example, f of x equals absolute value of x. The derivative of f of x equals absolute value of x doesn't equal 0 anywhere, so it doesn't matter which interval I pick. But we can see with Rolle's theorem, if I choose -2 and 2, the absolute value of both of those functions is 2. So everything about this stuff right here satisfies Rolle's theorem except the differentiable part. Has to be differentiable. Let's look at some examples of Rolle's theorem. Let's say f of x equals x squared minus 4x, and we're going to do it on 0 to 4. We're going to find where f prime of c equals 0, with c being in. Remember, that means in 0 to 4. It means element of, actually. but not important. N is it works just as well. So we're gonna first, with the way we do this, we show that f of a equals f of b equals 0. If I stick in f of 0, I get 0 automatically. 0 squared minus 4 times 0 is 0. If I stick in 4, I have 4 squared minus 4. That's 16. I'm sorry, 4 squared minus 4 times 4. 16 minus 16 is 0. So f satisfies the Rolle theorem because this is continuous and differentiable. And f of a equaled f of b equals 0. So there must be some c in 0 to 4 where the f prime of c equals 0. We can find it. We take the derivative, f prime of x equals 2x minus 4. To find those values, that absolute max or absolute min, we set that equal to 0. We solve. We find 2x equals 4, so x equals 2. And so if you did f prime of 2, you get f prime of 2 equals 0. 2 is in 0 to 4. We found it. Okay? Why don't you guys try doing this one real quick? F of x equals x cubed minus 9x on negative 3 to 3. Remember, you got to show that f of a equals 0, f of b equals 0. Make sure you point out that it's continuous and differentiable, and then find c. All right, I'll assume you did. We start off by plugging in negative 3 and 3. F of negative 3 is negative 3 cubed minus 9 times negative 3. You clean that up, you got negative 27 plus 27, that equals 0. We stick in f of 3 equal, so we stick in 3 into the function, we get f of 3 equals 3 cubed minus 9 times 3. 27 minus 27 also equals 0. F of x is a polynomial, which means it's continuous and differentiable everywhere. And so that's what I stated over there. This means it satisfies the Rolle theorem. There's a c in there. So take the derivative. Take the derivative, you get 3x squared minus 9, and you set that equal to 0. You solve, and you get x equals plus or minus the square root of 3. So it looks like we actually have 2 points. This is like a C1. Wow, that's a big old thick marker. That's like a C1, and that's like a C2. I like that. It's smaller. There's 2 C's that work for this. All right. Let's give you another one to try. F of x equals 2x squared minus 8x plus 6. We're going to do it on 1 to 3. Pause the video, work it out. All right. We're going to confirm the Rolle's theorem. We're going to do f of 1 and f of 3. If I plug in 1, I get 2 minus 8 plus 6. That adds up to 0. If I stick in 3, I've got 2 times 3 squared. That's 18. Then we subtract 8 times 3, which is 24. We add 6. That adds up to 0 also. Again, this is a polynomial, so it's continuous and differentiable everywhere. That means there's a c in 1 to 3 where f prime of c equals 0. So let's take the derivative. The derivative is 4x minus 8. We solve by setting that equal to 0. We get 4x equals 8, x equals 2. And 2 is definitely in 1 to 3. Okay, that's how Rolle's theorem works. In part B, we're going to do the mean value theorem.